All right, so in this video, I'm going to go over the solution to the cooling corpse problem, and then also hopefully give you some tools and strategies so that you can use those for application problems with exponential functions and exponential relationships. That way you can be successful when you apply exponential relationships to other problems. Okay, so the first question asks, and we're gonna, be thinking back to the story, the whole setup and scenario with the murder. Is there an asymptote for this relationship? If so, what does it represent? And if not, explain why not. So let's talk about what this relationship is. Remember that the coroner was murdered, and his body temperature is basically getting cooler and cooler and cooler. So when they're talking about a relationship, they're essentially talking about like as time goes on, so the independent variable being time, what's happening to the temperature of the body? So the temperature as time moves on. And so essentially we want to think in terms of like, well, I know that and guys, this is a rough sketch, it's not accurate by any means, but I'm thinking in terms of like the body might start at some temperature and then be cooling down. So is there a temperature that my body will basically stop cooling down? Is there an asymptote here where the temperature of the body is going to approach that but not get any cooler? And I think that the answer to this question is easier to think about in terms of like a cup of coffee. If you forget that you have a cup of coffee and you leave it out on your desk or something, it's going to cool to what? Well, it's going to cool to room temperature. And it's not going to get any cooler than that because essentially it's going to take on the degree of the surrounding environment. So the same is true with any temperature, is that it's going to cool or rise to the temperature of the room. Let's say you're thawing frozen meat or something, right? So it's going to come up to the temperature of the room and then essentially just level out at that value. So if you recall in this story, this was one of the first pieces of information given to us, and it's stated right here. I'm going to show you in the story because I like to be factual. It says the coroner's office is kept at a cool 17 degrees Celsius. So the room temperature is 17 degrees Celsius. So what is our answer to this question? Is there an asymptote? If so, what does it represent? And if not, explain. So the answer, very simply, is that yes, there is an asymptote. And it's the room temperature. So asymptote with a P. There is an asymptote at room temperature, which is 17 degrees Celsius. Okay, so essentially, and keep in mind that when I'm writing the equation for an exponential function, my asymptote is this plus k value right here. So that 17 degrees is going to be our k value. We're going to want to keep that in mind as we start building our function. All right, now it says make a sketch showing the relationship between the body temperature and time. What type of function is it, and justify your answer. So essentially, like we talked about already, and we might want to be a little bit more specific, I don't know, using T for temperature and little t for time might be a little bit confusing. So maybe we want to say that our time is represented in hours. And so we could say the temperature of the body after some amount of hours. So T for temperature and H for hours, something like that. And I mean, it's not going to look a whole lot different than what we had just done before. So 17 degrees Celsius is our asymptote, and then it's cooling something like this. So how do we know that this function is exponential? So it is an exponential function, but how do we know that? Well, temperatures are generally represented by exponential functions. Your temperature, whatever is cooling down or heating up, is generally going to happen somewhat quickly, and then it slows down as it approaches that room temperature. There is going to be, and this isn't like perfect because applied, real life applications are never totally perfect, but exponential functions model this kind of growth because generally the growth might happen quickly at first and then slow down as it approaches a singular value. So, I mean, a lot of times, in a perfect world, we might talk about like a common ratio or something like that, or some kind of a growth factor. Now, that's in like a perfect world. In this case, I mean, the body might not follow this perfectly, but we can create an equation that's going to model the situation using an exponential function. So that's kind of the difference between perfect, like a mathematical world, and then creating a model that sort of fits the data that we're collecting in real life. So exponential, essentially, because that temperature changes quick at first, and then it levels off at some value, which we would call our asymptote. So I won't take your time by writing that here, but essentially that's the answer. Okay, so now we want to use the data and the general equation AB to the x plus k to find the equation that represents the temperature of the body at any certain time. And this word represent, I've been using the word model. So either one is good. It's just this idea that like the real world data might be kind of, not a perfect fit, but this equation can model the situation. And so that's why we use these to model or represent the idea. Okay, so they're saying to use data. Well, what data were we given in the story? So I'm going to go back here and take a look at some of the data points that were given to us. So first things first, we want to look in terms of like a point, like hours, comma, temperature. So when we're looking for that, remember that hours is the independent variable, that's like our input, and then the temperature of the body is what follows. That's kind of the output. It's the dependent variable. If I said, oh, what temperature is the body? You'd say, well, it depends on the time. What time were you looking for? So in the story here, Agent 008 is taking the temperature of the body twice. The first time he takes the temperature, it's 27 degrees. And then it says an hour later, while they're searching for the tape recorder, so an hour later, he measures it again, and it's 24 degrees Celsius. So anytime you take your first reading, we're going to call that time 0. So at time 0, it was 27 degrees. That's just your initial temperature reading. And then after 1 hour, the next temperature reading was 24 degrees Celsius. Also, this is a side note, you could work in minutes if you want, and you would just say after 60 minutes, the body was 24 degrees Celsius. So it kind of depends, but once you choose your unit of measurement, you have to stick to it. I'm probably going to stick with hours because the number 1 is smaller and a little nicer to work with than 60, but I did want to just let you know that you can make that decision on your own. Okay. So those are the data points that we want to use. We already talked about K being equal to 17 degrees Celsius because of the room temperature. So now let's go back to our problem. The data are these 2 points, 0, 27 and 1, 24. Okay, so essentially, if you recall from one of our previous lessons how to solve this equation, I'm going to use these values as x, y, if I'm using this equation, right, x and y. You could also just call this, h and t of h. It's sort of up to you. Again, just how you want to label it. All right, the first equation I'll set up is going to use the first point. So I'd say 27, just plugging that in for my y value here, is equal to a times b, plugging in x, which is 0, and then plus 17, because we said that 17 was our asymptote. It's our k value. Okay, and then we want to start solving, so I might subtract 17 from both sides to start, and I get something like 10 equals a times, well, anything to the 0 power, think about that for a minute, is just 1. So essentially, I have a is equal to 10. All right, now I'm going to set up our other equation using the other point and this new piece of information I just found. So in this case, y is equal to 24. And then a is 10. I'm not going to plug it in just yet because I like to kind of see the point first. X is 1. And then k is 17. So if I want to plug in my a value, which I just found from over here, it would look something like 10 times b plus 17. B to the first power is just the number b. And so this is going to be pretty simple to solve. Let's start by subtracting 17. and I get 7 equals 10 times b. Divide by 10 on both sides, and b is equal to 0.7. Okay, so I essentially have my a value, which is 10, b is 0.7, k is 17. I can now write the equation for this problem. So y is equal to 10 times 0.7 to the x plus 17. And if we wanted to use function notation, because I kept bringing it up, it might look something like t of h, where h is hours after death, is equal to 10 times 0.7 to the h plus 17. So I just wanted to show you that there are a couple of options. If you want to use this, is way more contextual. It tells my reader its temperature in terms of hours. Using x and y is very vague and very general. It's not very specific. So you can use this or this. All right, so now we have our equation. Let's keep answering questions. So now it says, at approximately what time did Dr. Deadman die? So I really want to use my equation to figure this out. 0.7 to the x plus 17. So my goal is to use this equation and kind of work backwards. Sorry, I want to work backwards and find the hour that Dr. Deadman died. So let's think about that for a moment. I don't know what the hour is. That's what I need to solve. But do I know the temperature of the body? That's the only other thing I could plug into this equation, either time or temperature. Well, I do actually know the temperature of the body when it died. If I look back at the story, I get a couple of clues here. 27 degrees Celsius was 10 below normal. So I guess normal would have to be 37 degrees. So let's go back here, and I'm going to plug in 37 degrees. I want to know for what hour, at what time, was the body 37 degrees. So I can plug that in and then solve for h. Notice we're going to need to use logarithms to do that. So I'm just going to begin by subtracting 17 from both sides, and then divide by 10, and I get that 2 is equal to 0.7 to the h power. Notice this exponential, we really do need to use logarithms to solve for this. So I'm going to use that technique of taking the log of both sides. And I'm going to use a log of base 10 just because my calculator does that really easily. Something like this. I know from log rules that the exponent comes down in front. I have h times log of 0.7. Now guys, remember that log of any number, this is just a number, so I can treat it like one. If I want to isolate h, I'm going to divide by the number that it's being multiplied by. I'm only doing this because it allows me to have an exact answer as my solution, and I'm going to plug this into my calculator in just a moment. Okay. So now I'm going to take my calculator and type in log of 2, close parentheses, divided by log of 0.7 equals negative 1.943. So that's negative 1.943. Okay, and that's like kind of a weird answer, but remember what it represents. H is the number of hours. And I hope it feels okay to you that we're getting a negative answer. Because if time is ever negative, it just means we're going backwards in time. And that kind of makes sense because I want to know how long ago was Dr. Deadman killed. It's almost 2 hours ago. So let's be really specific here about solving that. This number is actually equal to 1 hour in the past, and then 0.943 of an hour. I want to convert that to minutes. So I'm going to multiply 0.943 times 60. Because 60 is 1 hour, right? 60 minutes is 1 hour. Well, I only want 0.943 of an hour. Not the whole thing, just only part of it. And it winds up being 56 minutes. So 1 hour and 56 minutes in the past. Okay, so now let's keep comparing because I need to talk about at what time did he die. The question really says at what time did he die. So the temperature, the initial temperature at time equals 0, that was actually taken when the security staff showed up at 5:12. So now I need to go from 512, I need to go backwards